doc with Luis, and we were actively involved in the development of the software, well, software and the hardware, that'll be at the end of this talk, for the Valkyrie robot at NASA. So that's largely what I've been doing for the last year and a half. Okay, so this is essentially preaching to the choir. I took a couple of these slides from actually an introductory talk I gave to one of Luis's undergraduate dynamics classes. But just trying to pose the problems that, as we all know, robots are really complicated systems. A lot of the things that we've been focusing on algorithm-wise are ways to achieve these autonomic functions that as people, we don't even think about it, like the balancing, the walking, the push recovery, that sort of thing. Also, natural collision avoidance, natural kinematic feasibility. Like if I need to reach behind me, I know I only have so far I can reach. So that's this is the sort of things that we call higher level planning algorithms. But there's also these intelligent functions that people just aren't, or robots just aren't that good at, but people can be really good at, like object identification, goal setting, like based on my environment, what should I do next to achieve my ultimate goal, that sort of discrete planning. And then, of course, discrete decision making. One of the major focuses of the software team for the Valkyrie robot that we were involved in was how do you integrate these two functions? How do you get an operator in the loop or let a series of higher level planners make some of these decisions and then modify your autonomic functions accordingly? Then other considerations, my background is actually developing simulation software. So for me, everything works perfectly. I love optimal control. It never fails. But in hardware, we all know that that's not generally the case. These issues with latency, sensor discretization, and servo rate, and then naturally, human operator sleep deprivation that we were all very familiar with after the DRC. So the outline, I'm going to talk about the whole body control algorithm, which is not necessarily new. What's new is the way that we've managed it, and we're currently in the process of expanding that tool to encapsulate other of these sort of low-level algorithms, inverse kinematics, other inverse dynamics, even optimal control. And we're calling this the rapid architecture, which is rapid application programming. So again, something that can evolve as your tasks evolve. And then Luis is going to talk a little bit more about the hardware that was developed. And there's a graduate student from our lab who was actively involved in the control of the series elastic actuators on the Valkyrie robot. Okay, so this is the way that the whole body control problem, this dates back to, I guess, what, mid-2000s, Yu and Osama and some other people working on developing this. Yeah, 2007, I forgot the exact date of that paper. So again, it's the floating base. And then the constraint formulations are on this velocity level. So it essentially, what the problem does is based on whatever information or plan you have, takes for granted that these velocities are going to be zero. And I'll show an example of where that's done based on measuring reaction forces before we undergo constraint switching. Then the task kinematics, instead of using the full floating base, we use this dynamically consistent constraint Jacobian. And then you end up with this prioritized control structure, so successive projections as needed. Clearly I'm giving a talk at the right time now that Chris is here. And again, this is done, the output is generally this acceleration term. I'm using P here for reasons that'll be obvious later. A lot of times this is X, this is your operational space acceleration. And then this lambda, again, is your constraint consistent mass matrix. Sorry, in gravity compensation, Coriolis compensation terms. So in the MultiContact framework, what do we do? Essentially, that controller gets augmented with the L star gamma internal. And those gamma, or the internal manifold of internal forces is defined by the joint torques which don't induce any motion of the system. And to do that, we use this construct which comes from essentially a haptics grasping community. So once you've established these contacts, you treat your robot as a big hand. and that lets you control these internal tensions, and you can use this to do things like prevent the feet from slipping, prevent the ankles from rolling, that sort of thing. So what can we do with this? This is actually not what was running, like many of you, not what was running on the robot for the actual challenge, but an algorithm that we were running. For us, it was pre-CDR. We didn't actually compete in the VRC, but we did, like, we tested ourselves with all the VRC. Yeah, exactly. We had to show all the same things anyways. So this is essentially a state space planner for the center of mass. It's based on essentially inverted prismatic pendulum dynamics. So we let the center of mass height vary naturally, and we just control. In our case, it was always a planar trajectory, either constant or based on some essentially linear trajectory when you're going up over steps, that sort of thing. And so we had a series of, our planner was essentially a finite state machine that transitioned us from, a forward, double support, so we could actually slow down our swing to make sure we didn't overshoot. And then the blue line there is this backwards dynamics of the pendulum, which is single support. And we always parameterize so that that COM position is along the trajectory connecting the centers of pressure between the 2 feet. So most of our dynamics look like that. Let's see, this video might not pop up in the right screen. Let me just get it over there. So this is our walking montage. And so basically what we did here is, like, the exact same code runs for all of these things, and we just actively re-parameterize based on force sensing, and then based on force thresholds. Once a contact has been established, then the next steps are planned according to where you've actually put the foot down. So it's just planning one step at a time. What's that? That was sped up. I think that when we were doing this, we ended up getting it running close to real time. Like when we were actually doing it, it took some tweaking and some Gazebo parameter tuning. What's that? That's like Gazebo hacking. Yeah, we did a lot of Gazebo hacking, but we did end up getting it to run at real time. You can see all of our little extra force sense. Was the video sped up? The video was sped up. Yes.
I think he's asking a different question.
Yeah.
If you actually ran this on the robot, how fast was
it's slower than that. This was actually sped up. Yeah.
Okay.
So.
Factor 2, 10?
I think like.
Look at the name of the video.
Yeah. Where does it say 2x? Yeah. So factor 2. Yeah, I can remember for this one exactly. Okay. All right. So that was state space planner. And then this sort of multi-contact example, that formulation, gosh darn it. I've been having this problem recently where it's not been popping up right. So this is again, the CarIngress example, where in this case, an operator, Steve Hart, for those of you guys who know him, was essentially planning these grasp positions. So, and once a grasp had been achieved, then it was switched to the next position, and the set of contacts or the set of constraints is switching every time you see the grasp switch. And I think there's one more here. Okay, so then this is kind of a segue into the next section of the motivation for creating a software infrastructure to manage this. So this is a combined example of essentially a hierarchy of planning algorithms. So this starts essentially with a footstep planner, and then that center of mass planner that I showed before is going to execute those footsteps and get it over to the ladder. And again, this has been sped up. And then once the robot is actually at the ladder, then, and this is again no real dynamic planning, it's essentially just a finite state machine of grasp positions and then motions relative to the hand, or like motions of the hip relative to where the hands are. or used to get up the ladder. And this sort of maneuver was enabled by the management, or this rapid architecture that I'm going to talk about next. Okay. So, right. So, as I said, for implementing these things, there's several considerations. So either planning algorithms, inverted pendulums, EMP, whatever you want to do, they need to be able to allow for constraint switching or constraint blending, depending on the type of algorithm you're running behind it, and also potentially sensor-based task re-parametrization. So I need to be able to switch what I'm doing according to sensor input and do it readily. Also provide interfaces for an operator front end. In this case, it's the RTC, Robot Task Commander. I don't know if you guys have seen those connected bubbles if you've ever visited NASA, but we set it up to interface with that. So then this essentially allows whole body control to run as part of a finite state machine in that context. We also were interested in introspection and diagnostics, so servo rate and controller states. Also, we've spent a lot of time, and our colleague, the other postdoc who's not here, Ling in particular, put a lot of time into optimizing the multi-threaded nature of this, because when you're updating your task goals and inverting those smaller matrices, there's a lot of really low-hanging fruit for speeding things up, so a lot of time was spent on that. And then I said the ultimate goal was this sort of rapid algorithm prototyping and development for field deployment, to be able to piece together new things on the fly, or let higher level algorithms piece them together and then just run it. So with that in mind, we kind of developed under the design principles of expressiveness. So we essentially need a sufficient number of primitives to enable us to do whatever, build into whatever behavior we need. This sort of multi-controller support, which, at the time we were building this, I mean, everybody here has computed a Jacobian, and everybody needs to know things like error and error dot. So if you're optimizing a framework for computing those things, why not give it a structure that allows you to apply it to any end application that you need? So we had that in mind as well. Again, performance with multi-threading, and then diagnostics, so introspection into your system state. If you're not achieving a task, if something's losing rank, to be able to have access to that as well. And the target audience is application developers. So people who maybe aren't necessarily interested in the whole robot dynamics problem, but are interested in using their path planning algorithms or some more intelligent algorithms, and just being able to run it and test it with something that works already. So we allow Python and C++ planners, well-defined interfaces for sensors. And then ultimately, we're working on developing something right now that we think will be useful for algorithm developers, which is most people in this room at some point or another in their careers. Oh no. Sorry, I was working on this figure actively. My arrows labels aren't showing up in this version, sorry. So this is the essential idea. We have these sort of application primitives, which are tasks and constraints, like what do I want to be doing, subject to what sort of, typically contact constraints, sometimes motion constraints, whatever else. And these primitive controllers are, for instance, your just like a PD controller for an acceleration, that sort of thing. It could be a pass-through layer if you're running inverse kinematics. Doesn't really matter. And robot controllers are things like the whole body controller, anything that does a lot of those hefty matrix algebra operations. So that's where your optimal control would go. So yeah, this is maybe a little bit too much detail. I think that a lot of this is obvious to most of the people in this room. But the idea is to provide, like I said, sufficient primitives. And then these primitives are parameterized by whether they're on or off, if you need a frame offset. Also, there's a lot of this talk of relative reference frames. If you just make that a parameter, and then you can automatically compute the Jacobians and errors in moving frames. Why not? And then selection matrices. think was it Tuan was talking about that, if you only want to control a position or an orientation, to be able to do all that math in one sort of simple, with a simple specification. And then we established these two essentially container classes, this compound task and constraint set. So this can store prioritization as needed, and then constraints are naturally the highest priority task. And you can also determine from this, so this is on the introspection edge, if you're losing feasibility, if you're losing rank, you can directly determine your MultiContact grasp matrix from your constraint set, that sort of thing. And so this is an example of what was running for the compound task for the walking that we were just showing. So first, the joint limit task, which is active if you're close to a limit and not otherwise. Then the feedback according to the inverted pendulum as a center of mass task is our highest priority. And then finally, the foot position. So, and we found it convenient to split the heading of the foot and the roll into different, so we could enforce different compliances on each of those. But it doesn't necessarily have to be split up that way. That's just a simplification. And finally, the torso pitch, the posture, and then our internal tension to keep the feet from sliding or the ankles from rolling, that sort of thing. OK. And then again, with the idea of multi-controller support, so we have these primitive controllers. And the essence of these is to take the fundamental state of your system, those operational states, and transform it into something that is useful for the robot controller that you're running at the end. So in our case, this is typically gains that give you a reference acceleration for the whole body control algorithm. But you can also put, for instance, weights for optimal control in here as well. And then these robot controllers are the things that generate the output that you want to send to your hardware. And several are implemented. I've actually been in the process of working at the optimal control version of this, and I was curious to hear about all of the different solvers that you guys are working on. I've been seriously toying with the idea of just implementing Gwen, which seems like it might be the way to go instead of using something off the shelf, but I'd be interested to hear more feedback on that. And then this is just following up on the example of given that we have this sort of autonomic function, the thing that will execute the torque commands. Now what you want to do is develop a planner that gives you tells you what primitives you need to execute to get your robot to do what you want it to do. So this is what we did for the swing planner. And then these are just the examples of parameters that were used to facilitate constraint switching and that sort of thing. So you can see force thresholds are actually important. Putting your foot down below the ground in order to make sure you've established contact. If you want to put your foot down and you don't touch anything, put it down further. That sort of intelligence lives there. OK. So, and then this is just for the actual challenge, we didn't end up running. We ended up splitting the robot into two pieces, and we were running inverse kinematics on the lower body, and then essentially a whole body torque controller on the upper body. And so we were doing the manipulation. So this is, again, have to get it up.
Some?
Hmm?
You have some?
No. You don't need to for this.
For the lower body, you were doing just position control?
Jordan could actually answer that a little bit better. He was largely responsible for implementing that, yeah. So this is just an example, again, of the front-end state machine and doing this task is scripted, but parametrized ahead of time. And so we weren't overly involved in the perception itself, but the point of this was to make the whole body controller able to easily receive commands that had been generated according to what the perceived working conditions were. And so this was just a test run that we were doing. I don't know if it's going to get any more exciting.
Did you guys find that doing force control in
science benefit from these tasks?
When it came down to it, we actually ended up making we had pretty high gains when it came to the even the manipulation task. I think that it did give us a little bit of benefit in that, like when we were, trying to place a hand on a valve or on a doorknob or something, we didn't have to worry so much about pushing ourselves over, because we were like really the lower body, like we ended up making it very stiff. So there was some benefit to it in that sense. Yeah. So I think that I'm going to pass it off to Luis after the next slide. If I can get back to the, all right. All right, so this is essentially what we've been working on now along with our cleanup effort, and essentially the plan is to open source that rapid package by the end of the summer, and try to sell it and make it useful for people who don't necessarily want to do the kind of algorithm development that we're interested in. But one of the major things that we noticed was we had impedance, the maximum impedance that we could achieve was really strongly limited by latencies and also by sensor noise. So we're working on studies right now that are trying to quantify exactly like the best way to tune your controllers in conjunction with how your actuators are tuned and everything else that you know about the system. So I think that with that, I'll hand it over to Louise, who's going to talk a little bit more about the hardware development that we were involved in. Yeah, sure.
So how robot agnostic is all this?
The idea is to make it robot agnostic. I mean,
Is it option?
we've implemented it. So this is running on Valkyrie. We have 2 other robots in the lab, and it's running on one of them, and it will soon be running on the other. So it actually is like becoming more and more robot agnostic. That's been our major effort since the.
Okay, so much for the story of simulation where things were ideal. And at a certain point in August, we started conducting real experiments. As you guys know, within the score point, we did participate. And I want to tell you a little bit of the pros and cons of the strategies that we follow. We develop great actuators. And these are rotary SIAs. You can see the spring here in the middle down. Actually, the one on the top right, it was inspired by a design in my lab by Nick Payne, where we use piston-like drive with driving the ball nut instead of the ball screw. So this is a SIA that is much more compact for the same amount of power they provide. So it's high power to weight ratio. And NASA liked it, as well as HMC. HMC produced several of them. Is Peter around here? Produce several of them now used in the Minas exoskeleton for the ankle joint because of the high compactness. NASA like it too. They did enhancements. The motor is actually surrounding, it's like sandwiching the ball nut. And that went into the ankle joints and into the torso. So we produce great actuators, efficiency, great force control in all these actuators as well with our work with low-level controllers together with NASA. We also produce quite a bit of innovation in high-performance WBC at about 400 hertz projection-based techniques using multi-threading. As Gwen commented on, we had great experience with programming interfaces. We developed planners based on RFSMs and both Python and C++. Lately, on a study on real-time issues, and I think I'm really very motivated by this issue. I am, by education, I'm an electrical engineer. I really like the effect of sensor noise, latencies, stability theory, and so on and so forth on the performance of these kind of big math problems that we have. And I'm also excited about the open source prospects of WBC in the summer. On the con side, we we were, I believe that we were the only brand new biped that competed there. And that was a challenge for us, although we were a very large team. But if you look at CMU and Robosimian, right, and JPL, they were quadruped robots in essence. And you know, there was a lot of hurdles, certainly, but they didn't have to deal with dealing with the disturbances, gravity disturbances, and for balancing and so on and so forth. Other bipeds, they had been there already before, prior to the competition. So we had to deal with this hurdle. We also went with a solution with full body CS, Sears elastic actuators. We had CS on the upper body and in the lower body as well. We actually had a phone call very early on in October with Jerry, and then we asked him if he would recommend using CS for the lower body, and he didn't recommend it. However, there was no particular reason why there was no details of why exactly it wouldn't be a good idea. Now, after all this time, we learned why, and the why is because of the inner force control loop that it makes the stability much more delicate and also much more susceptible to latencies. Now, it is great for me because this is now something that I'm publishing. It was bad for Valkyrie because it was a hurdle. It also played a role on the way we ended up in the competition. We actually removed all the springs on the lower body and went to the competition with inverse kinematics. And now they are back. Because of our efforts on improving communications and so on and so forth. We went to the competition with no gravity compensation. And not because of any particular reason, but because just we didn't have time to produce gravity compensation. So really it was the greatest advantage of having Sears elastic actuators on the lower body. It didn't really play a role when we were there. We went with large communication latencies, and I can still not say what were they during the competition, but I have the feeling that they were maybe beyond 10 milliseconds. And that is a major hurdle for good precision control and no gravity compensation, and the CS with the force control. We went there with no simulation after Gazebo 8.1, again, on behalf of the software. We stopped doing simulations after what you saw here. And we went to the competition with no INU post-estimation. Now, this tells us that we basically were coming there with a newly designed robot. And these are the kind of hurdles that you pay for going with that lack of experience. I think that NASA acting as consultants now will do much better in the next round. One of the great things about the actuators, all of them Sears elastic, is that we had great force control. In particular, we leverage our work from Transactions in Mechatronics 2013 in using disturbance observer. And here you see disturbance observer on the bottom. So we have a force. This is a force control. We have a typical PD controller, and disturbance observer is taking the difference between the reference torque and the output torque, and that's called the disturbance, and it's feeding it back to the desired torque and it's subtracting it, such that you modulate the desired torque with what the estimation of disturbance is going to be. And that adds a tremendous amount of disturbance. One of the things that we have done recently is define what we call the disturbance observer region of convergence here in gray, which defines the area where your closed-loop transfer function can operate, such that when you add a disturbance observer, you will converge to the ideal force transfer function with an error delta. So this is the robustness area, essentially. And in the right side, you can see the magnitude and the phase of different actuators with an unknown load. Basically, you're increasing the output load by, from fixing it to a very small inertia, and you have a perfect force tracking for any of these cases. So quite a bit of robustness. So we really had fantastic force control. Why it's not going forward?
Where's the frequency? Which frequency? I couldn't read it, sorry, my accent worked very well. What is the
It's 100, about 100. It's a little bit less than 100 hertz.
100 hertz?
Yeah, force feedback. So very, very nice work on the force level. You can see here two instances. On the left side, only a PD force control with expected errors. And on the right side, our controller, which it's arguably close to perfect. What you're seeing here is the cogging due to the harmonic drives. The same thing running on the series elastic actuators. The linear series elastic actuators will be a little bit higher fidelity. So this is very good force control, although it looks like there's a bit of ringing.
Okay, sorry.
Yeah.
How do you measure the bandwidth of your force tracker? What's the experiment that you use?
You run a chirp function. So you take the actuator in a test bench. You fix you fix the output to a load.
So you do a locked off experiment?
Yeah.
And what is the amplitude that you get? Did you send it?
The amplitude, this normalized, so I don't know what amplitude of force, but high, comparable to the applications that you're going to be using it for. But when you have when you fix the output, then you can have basically any magnitude that you want. But when you have it, when you have small inertias, you have to be careful because then you're going to accelerate very quickly. So you have to, do what you can without breaking the actuator. How do I run the video?
Click on the picture. Like with the arrow.
You click on it?
Yeah, and then that's what I was saying. It's popping up. It's not popping up properly for some reason on this computer. So go. Yeah, there you go.
And those are videos of an earlier version of the linear SIA that it was improved upon later on, and it was part of the Valkyrie on the ankles and torso. And what you have here is high power tracking performance. So relatively high weights at very high speeds. This is another one that I like more than this one. The one that is the high power test too. Yeah, that's one I like. So large weight, large speeds, and high precision, essentially.
When you're doing the position control, are you doing it on top of the force control?
Yeah. Yeah, we're doing it on top. And here we assume that we have perfect model because everything is very contained. The biggest challenge on SIAs is that your precision gains are much more reduced. It's much softer because of the inner force loop. And therefore, if you don't have a good model, then you're going to suffer from it. So much for force control. The truth is that the end-to-end position performance of all of these relatively complex math problems, humanoids, is far from ideal. And but however, more stability analysis are based on perfect feedback linearization, on no actuator dynamics, and ignoring latencies. One trick that we do is to have at the low level perfect force controllers, and therefore the dynamics of the actuator, the friction, for instance, it almost disappears, as well as the effect of the load inertia. And that kind of gives you a little bit of room for flexibility. But however, and here I show an airplane flying perfectly. This is the hypothesis that we make on end-to-end control systems. You have perfect feedback systems. But two problems arise. One is the hefty math. This is actually operational space control hierarchical operational aspect control according to Salini's notation, written as an optimization problem, and with inequality constraints as well. So it's just a way to see it. We know that this takes time. We don't know how much. Sometimes it takes, 5 milliseconds, 2 milliseconds, 10 milliseconds, whatever it takes, but it's a latency. But more than that is communication latencies. And those affect your controller in that you have now latencies on your velocity and your precision loops. And as well, we need to consider the effect of sensor noise, which is mitigated by having cutoff frequency in the low-pass filter. It turns out that these two blocks in this diagram greatly affect the maximum impedance of your actuator. As a matter of fact, they reduce considerably what you can achieve by almost linear dependency with the latency. Now, this is aggravated with the fact that SIA has force feedback control, which means that you're removing all the passivity of the SIA. A perfectly behaved force control actuator, it doesn't have any friction. And if it doesn't have any friction, it doesn't have any passivity. If it doesn't have any passivity, all your stability depends on your velocity feedback. But the velocity feedback is just a bad idea for stability because it's affected by noise. And what we saw in one of the talks that damping couldn't be increased too much was an HMC talk. It was exactly because of that. So latencies in the velocity feedback loop is just a terrible idea. And removing all the passivity from your actuator is also a bad idea. So my belief is that you guys, use, most of you, an Atlas robot. You actually were lucky that you had an imperfect force control and you had very high friction on the legs. These allow you to increase your gains and reject model disturbances and gravity disturbances in great ways. What we had is a very well-behaved force control robot, one of the best humanoids, force control humanoids. And that meant that all the burden of passivity, it was now on the side of the feedback controllers. And for that, we need to understand better what are the real-time aspects of all this end-to-end system, which is what we're doing right now. We are already publishing quite a bit. I think with those aids, Valkyrie is going to go beyond its current capabilities, as well as on improving the model. We didn't use gravity compensation last time. I think next time we will use it. And that hopefully will allow us to perform in better ways. You can see here crashing if you don't consider the problem in proper ways. And you can see this video on the web. But we did go to the competition, actually. Okay. And we did perform few tasks. We had terrific manipulation, in my opinion. We were doing host manipulation, door manipulation in great ways. As a result of using the SIAs and our delays on understanding stability issues, we had a very primitive control of the legs, and that didn't allow us to do balancing or locomotion. And with that, we couldn't really perform to a lot of the tasks. But that said, I think that we're in a position now that we will move forward and perform much better next time. That's it.